in bioengineering seminar series. Dr. Popa has a very long bio. I will just try to highlight the main point in his bio. So Dr. Dan Popa is both endowed chair of advanced manufacturing in the Department of Electrical and Computer Engineering at University of Louisville. He also is the head of the Next Generation System Research Group since January 2016. He received his PhD in Electrical Computer and System Engineering from Rensselaer Polytechnic Institute, RBI, in 1998. And his work is focusing on control and motion planning for robotics. Dr. Popa joined the Center of Automation Technology at RBI, where he was a research scientist working on over 20 industrial sponsored robotic research projects. After he moved to Texas in 2004, he became a faculty member in the Electrical Engineering Department at University of Texas. Dr. Popa is an active member in IEEE Robotic and Automation Society. He is also serving as associate editor in the IEEE Transaction on Automation Science and Engineering. This year, he is the chair of IEEE CAS 2016 conference. Again, thank you, Dr. Popa, and welcome.
All right, thank you for the introduction, and I'm going to try to speak up for everybody's benefit. All right, so I am brand new here. I'm happy to be at University of Louisville. My research group, Next Gen Systems, is actually made the transition here. I'm here with some of my staff and students. They're sitting in the front, and I'll acknowledge their work today in the presentation. And the other half of my group is left in Texas, still working on these things. A lot of the videos I'm going to show you today actually are recorded in our previous lab. So the presentation today is going to be about CoRobots that are soft and adaptive. So first of all, I want to start with defining what this is. So usually a soft robot refers to a robot that contains something that's compliant. Could be the actuators, the linkages, it could be the skin, the outer skin. In my presentation today, we're going to talk a lot about robotic skin. And CoRobot is a relatively new term that's been coined to reflect the fact that we would like these robots to cooperate, collaborate with people. In the past, robots were segregated in a certain part of the factory where humans did not have access, but in our future homes and hospitals, we're going to have these robots in close proximity. And the advantages, obviously, of CoRobots and also soft robots is that they will be safer, and they'll have better contact, physical and otherwise, and also, in the end, better performance. There are some challenges before these robots actually are deployed. They have to do with the long-term reliability, also the controllability and repeatability of these robots. They are softer, they're flimsier, they break down, they're not as accurate. But needless to say, there are lots of interesting applications from creating robotic pets to the next generation social and service robots. Also a big application in surgical robotics, robotic surgery, prosthetics, and also in industry. So my presentation today, I'll basically talk about our research in the area of adaptive, meaning the robot and humans adapt during the interaction. Physical, meaning they are in close direct contact. Physical human-robot interaction using soft robot skin. So I'll give you some examples from concrete applications, several projects that we are currently underway. And then towards the second part of the presentation, I'll talk about the technology. One of them is MEMS technology for sensor skin, and the second one has to do with the learning component, which we call Neuroadaptive control. And then I'll just conclude. So the goal of our work is to essentially create physical interaction which is adaptive. And this could be applied at any scale. I'm going to run some videos here so you understand. So at the large scale, first of all, this is my previous lab at UTARI Research Institute, where we have this robot called the Personal Robot 2. It's really massive, it's human size, and if you just want to push on it, it won't move. If you actually measure the force in the wrist and you close the force feedback loop, you can easily move it. And in this video, my former student here is moving it using something called impedance control, which is a classic control method in force control. And now what we want to do is, we would like this robot move the same way, regardless whether it's a strong football player that does this motion, or whether it's a child, 5-year-old child that just barely touches the robot. We'd like that robot to react similarly. So in other words, we would like the impedance or the admittance, for those of you who may be familiar, to adapt on the fly to the user. Here's an example of something similar in, this actually is an application at the mesoscale. People who use stages, micro-positioning stages, those come with very high gear ratios. They're usually not back drivable. You push on them, they won't move at all. But actually we have this force sensor here, and we're doing this active force compensation, and then you can just push these stages around to position them the way you want. So this was for a micro-assembly station. And then we can actually also take this to the even smaller scales. If you have a MEMS gripper with a force sensor at the end of this tip here, that's again attached to a robot. Somebody is driving it through a haptic device. So now you can feel the forces at the micro or nano scales. So this is done currently in atomic force microscopy. But the goal again is to adapt that impedance or the contact behavior depending on the task or the user. So this is not a new idea. I was doing this work back in 1995 in the area of basically this. I worked in spinal tap force control for spinal tap surgery. Essentially trying to replicate the field that a surgeon experiences when they insert a needle on an anesthesiologist in your spine. And back then we were doing adaptive force control. And what is new is that we have actually replaced the adaptive controller with a neuro-inspired feedback strategy called Neuroadaptive control, which actually works. I'll show you some example very well. Okay, so we have several projects sponsored by the National Science Foundation. You may know that there is a new program called the National Robotics Initiative. We had a project funded in 2012, which was in the first year of the NRI, that strives to create the skin and garments for the next generation robots. So the idea is you go to Sears, in 10 years from now, you buy your personal robot, you bring it home. This robot's going to have some skin, and it's not just aesthetically pleasing, but also it'll be sensorized with force sensors or proximity sensors, maybe even infrared sensors to see in the dark. And also you can have some clothes, and you may want to tailor it to your preferences, and these clothes again may have some embedded electronics. And what we're doing is we're looking at 4 fundamental issues which are related to each other. So what kind of sensors are feasible? Because in this scenario you need to wash them, you need to replace them, they need to be cheap, they can't be expensive. Also, where is it optimal to place them on the robot? And here, if you look at how our skin works, we have tactile discrimination, resolution of millimeter in our fingertips because we manipulate objects. But up here is basically about 1 inch, and back here maybe even more than 1 inch, because we don't actually do any kind of physical manipulation back here, so we don't really need that kind of resolution. So actually, the requirements for how to fabricate the sensors come from what kind of tasks are you actually we need to accomplish with these sensors. So robotic skin has been around for about 3 decades. People have described these MEMS or electronic skins with different capabilities. The only problem is that the requirements have been sort of chosen out of thin air. There's no basis for why we should have pitches of 50 microns, let's say, between different tactile sensors and so on. There's a lot of guesswork. So what we're trying to do is actually study the sensor placement to figure out what actually we need for different applications. We are also looking at this learning component. We do not want to pre-program behavior, and also we want to handle the fact that these robots will degrade over time. So we cannot just calibrate them once, install them, and then expect that they'll perform the same over time. And so we do that using learning algorithms. And finally, we work with some kinesiologists to evaluate these skins in clinical settings. We have 2 applications. One is embedding them in the prosthetic socket and also on the outside of a upper limb amputee prosthetic device. And the second one is looking at putting skin on the PR2 or U-Bot or robots that are suited for home robot, for home service robot application. And this is a summary of how we accomplish human-robot interaction with learning. The idea is that we use a neuroadaptive control scheme that's neuro-inspired, that has an inner loop and an outer loop. For those of you familiar with robotics, a robot is essentially a nonlinear system, a nonlinear plant, and you can characterize that plant. You can identify the parameters, so to speak. It's a arduous process, and it works well if the robot's stiff and it, the robot is well defined. But if it's a flimsy, soft robot, that's very difficult to do. Also, if you deal with materials which have hard nonlinearities like hysteresis and drift, that becomes really hard to do. So rather than doing that, we assume that there's absolutely no model, and we stick a neural network in this control loop, which essentially identifies the system. And now, people have used neural networks for model identification for a long time. The difference here is that we're not doing batch learning of any model. We're just sticking this here with some adaptation laws. And there's a Lyapunov function, for those of you familiar with controls, which guarantees that this actually works. So there is some guarantee that this learning scheme works. And in terms of learning control, there are 2 schools of thoughts that sort of diverged 50 years ago. There's the computer science folks that work on reinforcement learning. That's one method. And then there are people that branched into optimal control, adaptive control, the control community that actually, this work is inspired by the work of Frank Lewis and one of my collaborators. So the advantage here is that we don't need a robot model. We don't need actually also a task model. We don't need a sensor model. And we just actually have some guarantees that if we close the loop in a certain way and adapt the parameters, things will converge. So the inner loop, I described the inner loop. The outer loop, the role of that is to vary the admittance or the impedance depending on the task. And so the analogy I'd like to give you here is that you have a baseball player that's trying to learn how to hit the ball. They go through a 2-stage process. First of all, they go through an inner loop, which allows them to adapt to different weights of this bat. So you learn how to actually handle this bat. The second task would be to control the bat motion to hit the ball. That's this outer loop that I'm talking about. That's different. It's after you've actually learned the dynamics of the bat, you actually now want to actually accomplish the task of hitting the ball. So you go through this inner-outer learning stage. So this is sort of a natural fit with how we actually accomplish these tasks. I mentioned that we're designing and fabricating robot skin. So here we rely on a tool that we have created. It's implemented using a ROS, Robot Operating System Framework, and Gazebo. So it's actually, the intent here is to make it available in open source so that people can create new sensor models for robot skin and also apply it to different robots. We're fabricating skin sensors. Pictured here are tactile pressure sensors, which then have to be electronically conditioned and then deployed on the robot to close the feedback loops. I'll have more details about how we do the fabrication and the packaging of these sensors. Here's a packaged version of one of these sensors deployed on a mobile manipulator called the KUKA-bot. And these are sort of a visual representation of the simulation environment called SkinSim. Okay, moving on to other applications. We have worked a lot in the area of control, which is not necessarily physical, but it's from a distance. And so here, the pictures on the left show interaction between children and another robot called Zeno. This is the face of Zeno. And I'll just, I don't know if I can run this video, probably not, but I'll have another one later. So here, the idea is that humans and robot interact socially. And we close feedback loop based on certain markers on how the humans actually move. This is another social robot here at UofL. It is located in WS Hall, room 2018. It's called Philip K. Dick. Actually, it's based on the author Philip K. Dick with movie Blade Runner, if you remember that movie. It's actually a faithful representation of him when he was in his 50s by a robotic artist called David Hansen and his company. This is a prosthetic hand where the idea is to put skin sensors. So by the way, these skins cover the outer face of these robots. This is a healthy limb adapter. It's basically an adapter you can wear on your hand to drive this prosthetic device. I'll show you some videos. And this is another mobile manipulator which we are driving with these adaptive schemes called adaptive interfaces. So applications here would be treating cognitive as well as motor disabilities. Coming to the idea of an adaptive interface, these are some videos which sort of show you the point. In essence, we have a plethora of input devices. The iPhone, tablet, and all kinds of new cool gadgets, remote, that people use to control computer games or characters in computer games. So what, of course, we would like to use the same tools to actually drive the robot. The problem is a lot of these interfaces are hard to use or not intuitive. So let me show you an example through these videos here. So in this video with, again, the U-Bot, my student here is essentially driving the robot through a tablet interface. Basically, that's looking at mapping the tilt sensors of the tablet and also some other knobs that he has on the tablet to move this 7 degree of freedom arm and pick up objects. Okay, so he has to position the arm, close the gripper, then lift the arm, move the robot. It's actually quite complicated. And soldiers do this all the time to dispose of IEDs. Of course, the fastest you can do this and more reliably, the better. Okay, so the question that we're trying to address is, if you have an input device with M degrees of freedom and a robot with N degrees of freedom, how do you assign the mapping from M to N other than just guess that mapping? Okay, so again, the idea would be, how about if you can adapt that mapping on the fly, depending on what happens to help the user get better at what they're doing. Okay, so this would be one type of interface. There is another interface which we're interested in. This one is the direct physical interface. So here you are pushing and pulling on the robot to show it how to do a certain task, in this case, how to be a waiter. We're interested in the robot learning to go around this 8 track, and we're actually teaching it how to do it by showing. So you can do this with the base, and you can also do it with the arm by positioning the arm. Here's another video with a different robot, again the U-bot, but controlled with the Wiimote as well as pressure sensors. So in the case of the Wiimote, we have the divot in one of the in the nunchuck that can control the base, and then we have the accelerometers. We can control the arm, but it's actually not trivial to position that arm and pick up an object, just like that. And towards the end, my student Joe is actually going to also push the robot around directly through these 4 sensors that I described, robot skin. This is another robot. It's a military robot called the Dragon Runner. It's again with these 4 sensors placed on the robot, and also a tablet interface. You can drive this robot through the facility and have it help you. Perhaps you have a motor impairment. You can push the button to take the elevator, or it can even extend the arm to open a door for you. So the problem right now, if you deploy this technology, each robot needs a chaperone. That sort of defeats the purpose. If you need a chaperone for every robot, then you might as well do that task. Of course, there are people with motor impairments that need this help, so that would be useful for them. But we want to go to the next stage, where the robot has a lot of autonomy. It can do some of these things. Once taught, can learn to adapt and do these things by themselves. So here, the idea would be, of these adaptive interfaces, is that you pick an interface and then you observe the effect. If it helps the user, fine. If it doesn't, then you adapt that interface to minimize some kind of objective, performance objective. So I call that an adaptive interface. So based on these ideas, namely skin and adaptive interfaces, we wrote this proposal to the Partnership for Innovation program at NSF last year, and we got this project awarded, which now is going to come here to Louisville, and Speed School is going to essentially put together the next generation nursing robots in collaboration with 2 robotics companies. RE Squared is a manipulator company in Pittsburgh that has sold military robots for Afghanistan for IED disposal. So they specialize in very strong arms that can pick up a lot of weight and are modular. And then Kinetic North America is another defense contractor. They make the Dragon Runner or the Talon. If you have seen these robots in action, there are numerous videos on the web. Also very reliable, mechanically sound platforms. So what we're going to do is, using the help from these 2 companies, using our skin technology and our adaptive interfaces, we're going to put together this next generation robot. I'm not sure exactly what it's going to look like. It may look like something like the PR2, but perhaps it will have a chair and then you can sit in it, something like that. So that's the design work that we have to carry out this year. And we have a hospital partner in Texas. Again, I wrote this proposal before I knew that I would come here, but since then I actually visited UofL Hospital, and I'm hoping to actually test this here in Louisville as well. And we also have a partner at the UTARI Research Institute. They're going to help us with their existing robots like the PR2 that I showed you. So this project has just started. So let me show you next the video here. The PR2 in this video, we essentially taught him how to pour glasses of wine. And the way we taught him is by kinesthetic teaching. So we took the arm, showed it how to position the arm to pick up glasses or bottles. And then you can also program them if there are small changes in the position of these items. And also, the robot can push and pull, or be pushed and pulled by this cart. We actually served wine at a military event with 3,000 people. And the idea was, these were VIPs, and you could not. So those of you in computer science, I know you probably say, okay, so you use some kind of computer vision algorithm. So we said we cannot actually use any kind of vision algorithm because, probability of success is not 100%. That's one. Second is lighting in that arena, and there's a lot of noise and laser light. There's a laser light show. So, that essentially invalidates image processing and computer vision. So it's actually relying on mechanically registered things and relies on the repeatability of the robot, but in the end, it actually was very reliable. We poured 5 glasses. Actually, this will run. So what's the problem? I'll tell you a few issues here. So one is that these bottles cannot be full. The robot cannot lift at full extension a full bottle. It's too weak. Actually, it can only do half a pound or so of weight. And also, you notice it pours closer to the chest because that's where it actually can pour more weight. So that's one thing. And second, I showed you that we're not using any kind of active computer vision. I mentioned neuroadaptive control, and let me tell you what that leads to. So I mentioned this scheme actually can identify the nonlinearities in a robot, in this case the 7-degree of freedom robot arm. And if you do that, then a person here is actually guiding the robot on a circular motion. But the robot nonlinearities have been compensating using that neuroadaptive scheme such that the robot impedance or resistance feels the same everywhere in the workspace. So then it's very easy for somebody to guide that robot on a more precise task. If you don't do that, and you just try to apply that directly without compensating the nonlinearities, what ends up happening is that the person doesn't know where the stiffness is higher and will end up fighting with the arm of the robot. As a result, the trajectory is not the same. Okay, so that's sort of the idea. So even though you're trying to adapt to the higher resistances, you're going to end up fighting with the robot instead of cooperating with that robot. Okay, so main point here is by turning in that neural network, we linearize this highly nonlinear model, which has actually belts. It has a lot of compliance, and it actually has no known mass model, mass damping and gravity and so on. Here's the healthy limb adapter with the prosthetic hand. So this is my PhD student, Oguz Yetkin. And the idea is we want to test this for amputees, but before we actually recruit amputees and deploy this technology, I told my student to build this, well, he came up with the adapter, but I told him to wear this prosthetic device for 24 hours and try to do stuff with it. And here's some of the things that he can do. So first of all, we want to see how fast we can manipulate certain blocks. So this is called the box and block test. And he's actually driving the prosthetic through a reflected mirror device glove, which actually is registering his movements or pinch gestures. This was another prototype where he's actually just registering these touch events between his fingers and then creating grasp patterns out of that. And those of you familiar with prosthetics, those are driven usually using EMG signals, 2 electrodes, and it takes a long time for wearers to actually learn how to use it effectively. And the third video is again showing in a mirrored motion. Now we have flexion sensors in that glove, so that glove is sensorized and it's basically picking up position of the hand, and you can do mirrored tasks like carrying large objects fairly easily. But of course, the disadvantage is you have to wear this glove on the other hand, so there are some issues here to discuss. But idea here is you have a sensorized fabric, some sensors which help you drive the prosthetic better. So he carried all kinds of tasks like this and then timed himself and then offered this to other people and so on. And he's actually trying to finish his dissertation these days. All right, so I want to say a few words about social robotics. And I mentioned Hanson robots. This area of research has gone on for several decades. It started at MIT with Cynthia Brazil and Rodney Brooks. They had these robots. This one was called Kismet, first social robot, and this one is called Pog. And about 10 years ago, I met David Hanson, and this robot here in this video is called Albert Hubel. It was prototyped in our lab at UT Arlington, and then David took it to Korea. It was placed on a body at KAIST, Korea Institute of Technology, and it was paraded around the world, actually. And what you see here is that it's very realistic looking, right? It's kind of scary looking, and so it's a great vehicle to study this problem called the uncanny valley. So the theory here is robots get more realistic. If they are humans, then we're not scared, but if they are almost human, but not quite, then you go through this uncanny valley where you get frightened by them as if they're zombies. So you realize they're not human, but they can do almost the same things that we can. Well, so a lot of it has to do with what the robot looks like. So David actually came up and said there is no uncanny valley because if you make a robot that looks like Hitler, then everybody will be frightened. But if you make a robot that looks like Albert or Zeno, then it's not going to be scary for users. Again, very hard to test whether this uncanny valley theory is true or not because robots actually, you can tell they're not human. In order to make a robot be human, you need to take care of the appearance, okay? You need to take care of dialogue. You talk to it, it talks back. You need to take care of the facial expressions and also body language. And those have to be realistic as well. So there are 4 components, and what we do in our lab is we work on facial expressions as well as body language. I don't do much work with dialogue and natural language research or with appearance. This is another video which we can do here at UofL to essentially teleoperate PKD and reflect essentially our facial expressions onto the robot. I guess this is a very simple demo, but the challenge is actually, and I have a different video here that tells you there is some challenge here, not so much recognizing our expressions, but synthesizing the expression onto Philippe KJ. Because let's say you recognize somebody's smile, but then how do you make PKD smile? Well, PKD doesn't have the same anatomy. In fact, it has these motors in the skull that pinch the skin. And these motors are actually positioned in such a way that it's not easy to have one motor per expression. You have to combine a bunch of motors to get that expression. So in order to get that, what we do is PKD make faces. So essentially we run this for a while. We record what PKD's expressions are, and then we try to synthesize what the best way it is for a smile in essence. That's what it is, using, again, learning and a genetic algorithm. So you let PKD do these faces for a while, and then you essentially can synthesize a smile. And this is a video showing Sumit Das, my PhD student. He's here at UofL now. Actually, today he is down in Austin with Philip at South by Southwest, if you've heard of that event. I heard President Obama is supposed to speak today over there. But Philip is there, and Philip is actually puppeteered by some artists, theater cast. And we'll see what comes out from this event in Austin with Hanson Robotics. All right, I have some slides about what, how we do this. I think I will be running out of time. So let me actually show you another video with another robot called Zeno. Zeno is also here. So Zeno is a smaller replica of Phil. It looks like a child. It also has arms. And this is my son Alex, which is why I can show you this video. But essentially, we tested this robot with children in a motion capture lab. So Zeno says, follow my lead, do this, do that with the arms, and then we see actually what children do. And we were interested in whether there's a autism-related marker based on motion. So if children can follow the instructions of the robot, we wanted to know if there's a correlation with their autism severity. We had a sample size of 15 kids. Half of them were not autistic, the other half autistic with several degrees. What we notice is that there is a difference, similar to how autistic kids use the iPad. Essentially, when they're 5, there's a marked difference between a child with autism and somebody who's not autistic in terms of their iPad skills. By age 15, there is no more difference. In other words, children with autism adapt. So expectation is the same thing. We see the same effect here. And so the idea would be if you have this robotic therapy, since they're age 5, maybe when they're age 15, they will be able to actually make eye contact with the robot, follow instructions from the robot, and hopefully this will generalize to social skills. Now again, this is speculation right now. It's very hard to conduct these studies. But there are several groups around the country sort of working on robotic therapy for children with autism. All right, I have a few more minutes. So let me tell you about some of the technology behind all this. So one of them is this whole body robot skin. And again, the idea is that we record tactile and other forms of data from these distributed sensors. We are not only interested in the fingertips, but whole body skin. And lots of people have talked about advantages of this, going from learning to safety, performance, as well as operation in cluttered environments. This is very useful. So lots of researchers working with catheters and snakes for minimally invasive surgery have asked me for skins for the robots to figure out where the catheters are contacting different parts of the body. And if they had that information, they would be able to do a much better job doing surgery. As I mentioned, there have been many projects, about 30 years. For instance, this project had infrared arrays deployed on a surface, again, for robot surface. This was a project by Vladimir Lumelsky from the early 90s when he was at JPL. There are 2 European projects called Hexoskin and RoboSkin that are making these modules. These are triangles or hexagon loaded with sensors that can form a network and communicate sensor data of different kinds. DLR is a large consortium in Europe, German research institute that's also working on this. So what we are working on is similar in the sense that these sensors have to be modular, multi-modal. They have to scale in terms of the area to be deployed. And then they have to have some other additional properties. They have to bend and stretch, perhaps, and distribute computation. this one is a hard one, which is you have to be able to repair and replace them. If you spill the wine on PR2, then you should be able to take these off and put them back on. So we've actually prototyped some of these modules, pressure, force sensing, but also temperature, infrared, acceleration, and they are embedded in polymers. One of these polymers is the rubber material that is on Philip K. Dick's face. But there could be other polymers as well. And the way we manufacture the sensors is by a process called electrohydrodynamic printing. It's similar to inkjet printing with the addition of an electric field. And this can make very small features in the tens of microns, even lower. Essentially, you would have a liquid which comes out of the nozzle, and then you move the nozzle with the robotic stage. The advantage of this is you can deal with viscosities which are higher than regular inkjet printing. So Josh Baptist, who's sitting right here, is working currently on replicating this fabrication process at the MNTC here at UofL. In fact, he's already made some of the substrates. Next step would be to print this material. We're using this long name here, P.PSS, with some additives. And you know, this process is fairly sensitive, the one that I described. You have to set your DC voltage source and the spacing to the substrate and the speed of printing. And if you don't do it right, then something will go wrong and you lose your substrate. So we are actually working on replacing this with something else in this year. But Josh, I think, has been successful as of a few days ago making these electrodes already, and then interfacing them. That will be the next step to the electronic modules, which we call skin cells, and finally deploying them on the robots. So once the skin is made, we are interested in characterizing it. So this is a sort of a load cell setup where we're poking the skin to characterize the behavior. And what you see is, not surprisingly, a lot of these outputs, that is force sense per force applied or displacement, these are nonlinear materials. Okay, so this is hysteresis. You notice there's drift, and you know these sensors will degrade. Okay, so I mean, these are well-known issues. So rather than try to make the sensors better, more repeatable, which means probably more expensive in the end, how about if we can use our neural network learning to kind of compensate these nonlinearities? So if your sensor is crappy and the gains are low, then just adapt the gains, tune the gains automatically, depending on what happens later. Anyway, I don't really have time to go into this. We are also interested in reduced order models for these sensors so that we can study them in simulation. And there are 3 types of interaction models. These models that I described based on data collection. There are also admittance models, which are usually transfer functions. And also there are human activity models. So these are inspired by how actually humans apply forces to manipulate objects, and these are based on acquiring data during activities of daily living. So we are consolidating these models in the simulation environment called SkinSim, which is released, I mentioned, in the public domain using the ROS infrastructure. And the idea would be is that you can pick your robot. It will have a certain SDF format. You place sensors on this robot, and they could be different types of sensors. And then you, based on the sensors that you have, you measure interactions virtually in the virtual world using different model plugins. And then you close the feedback loop. And then you can study things like where should I put my sensors before you fabricate? How should I pick my spacing between sensors before you fabricate? You fine-tune your skins, and then you fabricate them and test them later. That's the idea in this environment. So we are interested in changing the sensor resolution, dealing with these nonlinearities, and dealing with things like spreading effects in these elastomers like rubber. So here you apply pressure, but some of it will get distributed through the soft material. Some will be lost, some will be sensed. And if you put it all together, we're interested in studying what the spacing should be between the taxels, what the size of the taxel should be, and drawing some conclusions. And again, I don't have time to, but typically, what I can tell you is this, based on what we have observed. If you look at different performance metrics, like in control, we look at steady state error, overshoot, and so on. The best sensors, the best scenario is when you have a huge single taxel in the same area, one sensor that covers that whole area. That will guarantee the fastest processing and acquisition time, the least noise, the smallest steady state error, right? So we don't need arrays, right? We just need one. That's huge. There's a problem with that, right? What's the problem? The problem is you have to put them on curved surfaces. That's one. And the second is you have to estimate what the center of application of that force is. And so the more taxels you have, the smaller the sensor, actually, the better that estimation of the center of pressure. So there are trade-offs, in fact. And what we are trying to determine is essentially what's the right resolution depending on the task, given some constraints of noise, data acquisition time, and losses, etc. So I don't have much time to go into details. A little bit about, before I conclude, about this neuroadaptive controller. This is sort of an adaptive control scheme where you're adapting the control scheme as well as the admittance. And the controller works by inserting this neural net and having a Lyapunov guarantee that this actually works. And the way Frank Lewis, who I collaborate with, puts it, this is sort of works like magic. You plug it in and you turn it on and it works. Okay? So unlike reinforcement learning, this scheme actually has some convergence guarantees. And then the outer loop is adapted using recursively squared in this case, but it works on essentially making sure that a human here and this adaptive model, when you put them in series, they will match a certain task model that you prescribe. It's the same idea in model reference adaptive control. So here's the human, and the human can change. The problem is we don't know what the human is going to do and how they perform the task, and we'd like to adapt this impedance based on what the human does given a task model. And again, we have papers where we show that this actually works with the PR2. And my student Sven is actually currently working with the PR2 to complete a paper on the outer loop and the robot's sensor calibration, showing that this actually works better than no adaptation or set impedance for certain tasks. So I'd like to conclude. Basically, I showed you some examples of some of the work that we're doing with adaptive CoRobots. The key here is that we need these advanced materials and embedded sensors for the next generation robots. We need to deploy modeling and visualization tools in the open source domain so that this activity can actually distribute among other researchers. So ROS and Gazebo are great platforms for standardization. And another key component of this is adaptation and learning is key. If we cannot adapt and learn, then these robots will have to be pre-programmed, which is a losing proposition. So in future work, we want to refine these game designs, make them cost effective, and also commercialize this technology. We also want to expand this neuroadaptive control and simulation work with more skin models, sensor models, and so on. And another exciting project is a nursing project that's just getting started. So we want to deploy this technology in two scenarios. One is called Robot Sitter, the other one is called Robot Walker. Robot Sitter will sit with the patient and bring them a glass of water or the remote control. And if the patient gets combative and wants to get out of bed, then the robot will say, "Nurse, come to this room," or something like that. Try to scare the patient. And then the walker will help the patient get out of bed and walk them down the hall. If we can accomplish these two things, I'm told by lots of nurse researchers that they will buy lots of these robots, and every hospital will have one of these robots in use in a few years from now. So that's all. I'd like to acknowledge the support from the National Science Foundation and from Kinetic North America, Hanson Robotics, and I'd like to acknowledge my long list of students and staff, without which videos would not be possible, and they are sitting here today, some of them. So thank you for your attention.
Questions?